Good morning, everyone. This is G. Narsimhulu, Associate Professor, St. Peter's Engineering College, Hyderabad. Today, we are going to discuss about discuss about the CB configuration of a BJT and its input and output characteristics. In last class, we was discussed about what are the different transistors like NPN transistor, PNP transistor, and what are the different configurations and how you can have the notations to determine these terminals of the transistor. Today we are going to be discuss about one among the three configurations, that is CB. CB is nothing but common base configuration and its input and output characteristics. Generally, you know that one in common base configuration, base is grounded. Base is going to be common to the emitter and collector. Okay, irrespective of the NPN transistor and PNP transistor, base is going to become grounded. That is called the common base configuration. Let us look into this. In this NPN transistor, the base is connected to the ground. Okay, and you can understand when you are working with the active region of the common base configuration, you have to be apply the DC supply like this. Means VAE having the plus polarity as well as the minus polarity. Plus polarity you have to be connected to the base terminal. Generally, now in the NPN transistor, base terminal is P, emitter terminal is N, collector material is N. So plus is connected to the P and minus is connected to the E. Then you can be say it is having the junction between the base to emitter, that is the emitter base junction is going to become forward bias, and corresponding to the BC, or you can be say it is a CB, collector to base junction. Okay, having the power supply like this externally, plus terminal to the N type material, it is now acting like a collector, and minus terminal is connected to the P type material, it is acting like a B. When you are applying in this way the power supply to the collector and base, means plus was connected to the N-type material, minus was connected to the P-type material. The junction which is formed between the collector and base, which is acting like a reversed bias. So you should remember it is having the two diodes which are connecting back to back. Base to emitter junction, it is having one diode. Base to collector junction, it is having another diode. Base to emitter junction diode is going to be acting like a forward bias, and base to collector junction is acting like a reverse bias. Appropriately, we have to be give the power supply like this. You should remember the polarity of the power supplies. What polarity of the signal we have to be applied to the base as well as the emitter as well as the collector to make it to satisfy the criteria of base to emitter junction is forward bias and base to collector junction is reversed bias. And let me consider PNP transistor also same like this. In PNP transistor what happened? PNP, emitter having the P-type material and base having the N-type material and collector having the P-type material. We have to be make it to forward bias of the base to emitter junction by applying the external power supply. How the polarity is changing now. When you compare with the NPN transistor, here PNP transistor power supply polarity have to be changed, because plus is always need to be connected with the p-type material, minus is always connected with the n-type material to make that corresponding junction diode into the forward biased. And another one at this side, what happened? VCC. Here plus is connected to the N and minus is connected to the P-type material, means the junction which is forming between the base to collector is a reversed bias. You should always remember that one. If you want to make that junction need to be forward bias, how to be apply the plus terminal voltage of the power supply to the P-type material, minus terminal voltage of the power supply need to connect with the N-type material. If you need not to be conduct that particular junction, means you have to be make that junction need to be convert as a reversed bias, how to be exchange the polarities. Like you know that one N-type need to be connected with the plus terminal and minus you can minus polarity of the battery you can be connected with the P terminal. Then the particular junction is going to become reversed bias. And input output characteristics of your transistor. What is the input output characteristics? Now let us look into this. Where is the input? Input you are giving between the emitter and base. Output you are collecting from the collector and base. When you are working over the input characteristics, you should be understand what is the voltage you are applying between the input terminal, means between the emitter and base, and what is the amount of current which is passing through the emitter terminal, that is the input current. Okay, while keeping collector to base voltage is constant, that is called the input characteristics. You are going to be monitoring while keeping collector to base voltage is constant and varying the emitter to base voltage and observing the emitter current and plotting the graph. Okay, IE versus VEB while keeping VCB is constant. That is called the input characteristics. In input characteristics, you are taking over the x-axis is VEB, over the y-axis is IE. The amount of current which is passing through the emitter terminal, it is in the milliamps range only, not like amps. Here the amount of voltage you are going to be applying to the emitter to base terminal is volts only. Here you should be observe, this is emitter base voltage over the x-axis, emitter base current over the y-axis. Emitter base current itself, it is nothing but emitter current. Emitter base voltage is nothing but you are applying the voltage between the emitter with respect to ground. Base terminal was grounded, means you are applying the voltage between the emitter and base. By varying the emitter base voltage, you are observing that how the conduction is takes place of the emitter to base junction diode. Means input characteristics are nothing but it is a forward biased diode characteristics, because you are applying the voltage appropriately to make that one emitter to base junction need to be forward bias. Then you have to be observed in this diagram here, just you have to be observed here, you are keeping VCB is equal to 5 volts or VCB is equal to 10 volts. Let me consider VCB is equal to 5 volts. Here you should be observed, here the input current is remain 0 until certain voltage of the applied input. Then after certain voltage applying, then input current is rising like this. This is a point where you can be understand it is a cut-in voltage of that junction forming between the emitter to base. Here also you can be observed when you applying the VCB 10 volts constant, it is going to be maintains a zero current of the emitter terminal until certain voltage of the EB. After that is going to be rising the current. means it need to be satisfy minimum voltage requirement to make the diode into the forward bias. Then only you can have the diode is going to become conduct, and consequently you can have the current passing through that junction. That current you can be call it as a emitter base current, or you can be call it as a emitter current. Here you should be understand the amount of change in VEB, the amount of change in emitter current, means the small amount of change in VEB after cutting voltage, you can have the large amount of current passing through the emitter, it changes. The relation between this, you can be determine that one what is the input resistance of your CB configuration. Here this is nothing but it is a input resistance of your uh, transistor. While keeping VCB constant, you are understanding that one amount of change of the VEB, and correspondingly what is the amount of change in emitter current. You should understand after cutting voltage, that is nothing but you can also call it as a barrier potential. It is normally 0.7 volts minimum you should be applied to make the diode need to be conduct for the silicon material, 0.3 volts for the germanium material. What is the silicon material and germanium material here? The silicon material which is using to form a junction. Silicon material is a semiconductor material you are using to prepare or to manufacture p-type material and n-type material. If you design the total transistor with the silicon material, then you have to be minimum supply voltage is 0.3 volts to make that semiconductor device or a junction diode to be conduct. Sorry, 0.7 volts. For the germanium, it is a 0.3 volts. Next, you have to be observed. It is having the small slight increase of the emitter current with increase in the VCB. It's not much change of this VCB effect over the emitter current. Here this is due to the change in the width of depletion region in the base region under the reverse bias condition. Just you have to be understand VCB was applied between the collector and base, okay, which is not impacting over that much over the emitter current. Only VEB is going to be impacting over the emitter current. Just you have to be observe this diagram. Here depletion region width is going to be changed according to the external power supply. The depletion layers was there between the base to emitter junction, between the base to collector junction. Okay, when you have this one, applying the voltage to the emitter to base, okay, which is need to be making this junction is forward biased, the depletion region will become narrower. The width of the depletion region at the junction of emitter to base will become narrower. So more number of electrons are going to be coming to the p-type and is going to be recombined and uh, uh, producing the base current. Okay, then when you say that one, here this is a voltage, it is applied between the collector and base terminal. Here it is the reverse bias voltage. Because of the reverse bias voltage, the depletion region corresponding to the collector and base will become larger. The width of the depletion region will become wider. Though you have the current passing through the collector because of the diffusion of the electrons from the base to emitter. This thing will again discuss when you are going to be having the discussion more over the output characteristics. Yeah, just you can be observe here, this is the depletion region width, it is increased. Early effect. You should understand when the reverse bias voltage, that is VCB, whatever you are giving externally power supply, increases, the width of the depletion region also increases, which reduces the electrical base width. It means that when depletion region is extended in the collector place as well as the base place, the depletion region extended lesser into collector area and more into the base area. Why? Because comparatively base material and collector material doping level is very high compared to the base material, so that the depletion region is going to be extended more into the base material. This effect you can be call it as a early effect, or you can be say it is nothing but base width modulation. It means base width also going to be changes according to the external power supply between the collector and base. Output characteristics. Output characteristics, you are going to be determining the relation between the collector to base voltage as well as the collector current. You are going to be observing that how the collector to base voltage is going to be impacting over the collector current. You should be understand, collector to base voltage, it is not impacting over the collector current. I will explain you how. You see, let me consider here IA. Here, this one is I, emitter current. When emitter current is not existed, means you have not given any external power supply between the emitter to base junction. Then only this condition is going to be possible. When emitter current is not existed, there might have some current passing through the collector to the base terminal. That current you can be call it as a ICBO. I will explain you what is the ICBO. Okay, and when you increase the emitter current, means when you are applying the external power supply in between the emitter to base, the collector current also increasing and maintaining constant with respect to emitter current. You see, here the collector current is equal to the emitter current. When though you are changing the VCB, it is not impacting over the collector current. It is just following the emitter current. It is having mathematical proof how it is having the relation between the emitter current and collector current. When you say that one emitter current is 2 milliamps, even collector current is also 2 milliamps. And emitter current is 3 milliamps, collector current is also almost 3 milliamps. Emitter current is 5 milliamps, collector current is also almost 5 milliamps. Is it not having any effect of the VCB over the collector current? Yes, we can have the effect, but it is very small. It is very small. Just to see this one here, change of the VCB and change of the emitter current. It's very small. Wider change of the VCB will be impact over the smaller change in the emitter current. Emitter current is almost, collector current is almost equal to the emitter current. This region, you can be say this region, total region is called the active region. In this active region, collector is always follows the emitter current. That collector current is not going to be impacted by varying the collector to base voltage. This region, it means that the region below the emitter current is equal to the 0. That region you can be call it as a cutoff region. In this cutoff region, there is no emitter current. Obviously, when there is no emitter current, though you have the VCB, there is no conduction of transistor. Here, generally, you know that one, Here VCB, it is having the positive voltage. Means positive is connected to the N terminal and negative is connected to the P terminal of the junction forming between the collector to base. The base is reversed bias. Though it is already the base to collector junction is reversed bias. Now if you have this emitter current is 0, by having the no voltage between the emitter to base, means that is a you can say the conduction or the operation region of this transistor is cutoff region. There you could understand that one, both junctions are reversed bias, or both junctions are in open circuit, act like a open circuit. Next point, this is a region, you can be say, this is a region, you can be say it is a saturation region. In this saturation region, collector current is goes on increases. Here what happens is, you see this one, saturation current goes on increases. You see that one, the polarity of the VCB, it is 0, it is -1. It's when you are going to be extend like this, it is nothing but more negative voltage. You can have the more saturation current. Just you have to be observed in reverse order. When you have the more negative voltage, you can be understand it is lesser current. Lesser negative voltage, you can be understand it is going to be equal to the emitter current. This is how the CV output characteristics, which was drawn between IC and VCB while keeping IE is equal constant. IE is constant mean VEB you are making it is constant. If suppose if you goes on extending the VCB, what happens? We'll discuss. Here output characteristics also you can be say it is a characteristics of reversed biased diode, because you are working with the collector to base junction. Collector to base junction always it is in the reversed bias. We are going to be monitoring the collector current with respect to change of the collector to base voltage. Here output characteristics has three basic regions: active region, cutoff region and saturation region. We already explained. In active region, emitter base junction is forward biased, collector to base junction is reversed bias. In cutoff region, emitter base junction is reversed bias, collector to base junction is also reversed bias. In saturation region, emitter base junction is forward bias, collector base junction is forward bias. Then you can understand the current relations between the collector and emitter. In common base, you can have this base is grounded, this one. What is the input current? It is the emitter current. What is the output current? It is the collector current. The output current divided by input current, it is a current amplification factor of this your common base transistor. The alpha can be noted like IC divided by IE. IE is nothing but output current of the CB configuration and IE is nothing but input current of the CB configuration. Alpha typically it is equal to the 0.90 to 0.99. It means it is almost equal to the 1. Means IE is equal to IC. You can also understand here. Here base to emitter junction is forward bias and collector to base junction is reversed bias. The IE is the emitter current. Okay, part of that IE is going to be moved to the IC, that is alpha IC. And one more current you can be observed here, ICBO. When this ICBO is going to be existed, this is a collector to base current when emitter to base junction is open. Like collector current is equal to the IC is equal to the alpha IE. It means that alpha is nothing but part of the IE plus ICBO. ICBO is nothing but it is a leakage current basically. When there is no existence of the emitter current, there might have the collector current is due to the leakage. That's what ICBO is giving. It's very small even. IC is equal to alpha IB plus IC, because I is equal to IB plus IC and ICBO. Just you have to be written like this formula: IC is equal alpha divided by 1 minus alpha IB plus 1 by 1 minus alpha ICBO. You should be understand ICBO is nothing but leakage current between the collector to base when emitter terminal is open. Emitter terminal is open means there is no power supply between the emitter and base. So if emitter current is 0, the collector current is simply ICBO. It is the leakage current between the collector to base. Then you should understand that one dynamic output resistance. It is the ratio between the collector to base voltage to the resulting change in the collector current while keeping constant emitter current. That is, you can be write like R0 is equal delta VCB divided by delta IC at I is equal constant. As I increases, IC also increases. That's IC depends upon input current but not on collector voltage. Like you know that one collector to base voltage. That you should be understand input current controls the output current. That means this is a trans resistor. Trans current you have to be understand. Since the transistor requires some current to drive it, it is called the current operating device. Means you should understand the transistor is a current operating device, not voltage operating device. Obviously, you might thought that one I is depends upon the VEB. No, yes, I is depends upon the VEB. Okay, but IE is not depends upon the VCB. Even IC is also not depends upon the VCB. IC is only depends upon the IE. IE is depends upon the VEB. So I is going to be giving the driving force to having the current in the collector terminal. Now let us go through this. If suppose if VCB your goes on extending and VCB your goes on giving more voltage, more and more voltage to make that one collector to base junction will become more and more reversed bias. What happens? We can have the breakdown of the junction. Like you know that one if you have the reverse voltage is more of the PN junction diode, then it is having the breakdown. So you can have the larger current is going to be passing through the diode in the reversed bias also. Here you have to be understand in this here VCB maximum. This is a maximum allowable voltage you can be give for the collector to base junction to make it to retain in the reverse bias. If it goes on extending more than that VCB maximum, the breakdown happens in the junction so that you can have the highly saturated current is going to be passing through that even reversed biased junction also. This is related to the input and output characteristics of the CB configuration. We'll discuss more and more about the another configurations in next video. Thank you.